Hello friend, welcome to this lecture. In this lecture we will continue our study of phase portrait for the linear system. If you recall, we were discussing the different cases. If you recall, we have this system of linear differential differential equation x dash equal to fxy and y dash equal to gxy. It is a non-linear equation, and then we consider the corresponding linear system like x dash equal to ax plus by and y dash equal to cx plus dy, and here it is clear that 0 0 is a critical point of this. And if we assume that this condition that a b c d determinant of this is non-zero, then 0 0 is the only critical point of this, and then we are checking the say behavior of the critical point, whether this critical point is a node, say stable node or unstable node, saddle point, or say center or whatever. So, depending on the eigenvalue of the determinant of the matrix A, B, C, D, we are trying to find out the behavior of 0, 0. So, we have discussed 4 cases based on this, and now we are considering the 5th case corresponding to that result. So, in this case 5, we are considering that the roots are purely imaginary, means first of all they are complex. So, it means that lambda you are writing as a plus I b and lambda 1 and lambda 2 is equal to a minus I b, where a is equal to 0. So, it means that real part is 0 here. So, if the roots are purely imaginary, then we are claiming that the critical point is a center. Now, what is this center? We will look at here. So, here if real part of lambda 1 and lambda 2 is 0, then we can say that your eigen values are lambda 1 equal to I beta and lambda 2 equal to minus of I beta, where beta is a non-zero real number. And we may say that our solution may look at as this: x equal to k1 cos of beta t plus phi 1, y equal to k2 cos of beta t plus phi of 2. And for that we have utilized our equation number 14, which we have already discussed. Let me go to the equation number 14 here. First, our solution will be looking like this as given in 11. Then we simplify and try to convert into this format, equation number 12 here, and then we further simplify and we can look at here as x y equal to k1 e to power alpha t cos of beta t plus phi 1 and y equal to k2 e to power alpha t cos of beta t plus phi 2, where this alpha is a real part of the eigenvalue. So, if this part is gone, then x is your k1 cos of beta t plus phi 1 and y equal to k2 cos of beta t plus phi 2, which is what we have written as equation number 17 here. So, x equal to k1 cos of beta t plus phi 1 and y equal to k2 cos of beta t plus phi 2, where this k1 and k2 phi 1 and phi 2 are already defined as before, and it is clear from this equation number 17 that x and y are periodic function of t. If you look at here, and if you simply say that if you replace this is your x of t. So, x of t is equal to k1 cos of beta t plus phi 1. So, if I look at x of t plus 2 pi by beta here, since beta is non-zero, so we can write it 2 pi by beta, and this is what k1 cos of beta, now t plus 2 pi by beta here plus phi 1. If you simplify, what you will get? You will get k1 cos of, and here it is beta t plus phi 1. Similarly, we can see that y of t plus 2 pi by beta is same as y here. So, it means that 2 pi by beta is a number. If we say that x t plus 2 pi by beta is same as x, and similarly y of t plus 2 pi by beta equal to y. So, it means that there exists one say t such that x of t plus small t plus capital T is equal to x of t and y of t plus capital T is equal to y of t. So, it means that the minimum of such possible t's, capital T, will give you the period of this solution x and y here. So, we simply say that from these equation number 17 we can conclude that x and y are periodic function of t, and hence the paths are closed curves surrounding 0 comma 0 here. So, one thing is very much clear here that 0 0 is a critical point and the solution will say form a closed orbit here, that we have already discussed, that if they are periodic they correspond to the orbit which is closed here. Now, members of which are arbitrarily close to 0 comma 0, that will depend on the values k 1 and k 2 here. So, also they do not approach the origin x as x and y oscillate between k 1 and k 2. So, it means that though they will very near to origin depending on k 1 and k 2, if k 1 and k 2 are very small, then they are very near to origin 0 comma 0, and but they do not approach the origin as if you look at as t range from say initial point to infinity, you can say that the value x and y both are oscillating value, and x will take a value between minus k 1 to plus k 1, and y will take the value from minus k 2 to k 2 depending on the value of t here, and hence we can simply say that by definition 0 comma 0 is a center here. And now we simply say that this is a stable center. Why we say that if we take any solution near to your orbit here, if you take any initial point here and take a orbit say passing through this, then it will follow almost this kind of path. So, it means that they exist an orbit which is passing through this, and it will remain always close to your the orbit which we are considering as first solution, first orbit. So, it means that if you take two orbit which are close to each other initially, then it will always remain close to each other for future time also. So, here in this case your orbits are center, orbits are closed curves, and critical point 0 comma 0 is a center which is a stable center, and since the path do not approach origin, the critical point is not asymptotically stable, though they are though critical point is stable, but it is not asymptotically stable because your paths are not tending to or approaching to 0 comma 0 here. So, let us have one example based on this. So, draw the phase portrait for the linear system y 1 dash equal to y 2 and y 2 dash equal to minus 4 of y 1. So, here we can simply say that 0 0 is a critical point here, and we can easily check that 0 1 minus 4 and 0, and if you simplify, find out the determinant here, determinant is coming out to be 4, and hence we can say that 0 0 is the only fixed point, right. Now, then next thing we want to find out is the eigenvalue corresponding to this, and if you find out the eigenvalues are coming out to be lambda 1 equal to 2y and lambda 2 equal to minus of 2y. So, here if you look at your beta is equal to 2 here, right, and alpha is equal to 0. So, we can say that your solution x is written as k 1 cos of 2t plus phi 1, and y is written as k 2 sin of 2t plus phi 2, right. And so, here whatever we have given, then we can simply claim that since eigenvalues are purely imaginary, and hence the critical point 0 comma 0 is a stable center here. Now, let us look at the behavior of the orbit here. So, if you look at x equal to k 1 cos of 2t plus phi 1 and y equal to k 2 sin 2t plus phi 2, we can simply rearrange this cos, and we can simply say that I can simply rewrite this y as k 2 cos beta t plus phi 2 as k 2 sin 2t plus phi 2 here, maybe you can write it k 2 tilde here. So, here we can simply say that I can write x upon k 1 equal to cos of beta t plus phi 1, and we can write y upon k 2 tilde equal to sin of beta t plus phi 2 here. So, here we can simply say that here the behavior is so the orbits are looking like the ellipse here, right. So, I am not giving the exact say here, but you may try this. So, in this kind of cases your orbits are close orbit, and here we can see that the orbits are ellipse kind of ellipse kind of curves here. Maybe you can find out the orbit here, or for example, if I want to find out the orbit here, let us look at here. Here we have your dy dy by dx. If I look at here dy by dx, I can write it minus 4x upon y here. So, I can write it here y dy plus 4x dx equal to 0. So, it is what y square upon 2 plus 4x square upon 2 equal to, say let us call this as c square here. So, here we have y square plus 4x square equal to 2c square, and if you look at carefully, if c is non-zero, then this will represent the equation of ellipse here. So, it means that in these cases when origin is a center, we can look at that the ellipse that your orbits are nothing but say ellipse kind of a figure here, and we can consider the circle as a kind of a type of ellipse here. Okay. So, so here we will conclude that if eigenvalues are purely imaginary, then critical point is a center which is stable here, and it is not asymptotically stable here, and we have seen one example in this case also. Now, if we summarize whatever we have discussed so far, so we can summarize in the given theorem that for the differential system 1, that is x dash equal to ax plus by and y dash equal to cx plus dy, let lambda 1 and lambda 2 be the eigenvalues of the matrix A, where A is the matrix given as A, B, C and D. Then the behavior of its orbit near the critical point 0, 0 is as follows. So, we simply write stable node if lambda 1 and lambda 2 are real, distinct and negative. So, here this will give you the case 1 here. So, here stable node if lambda 1 and lambda 2 are real, unequal and negative, and it is unstable node if lambda 1 and lambda 2 are real, unequal and positive. So, this will be your case, this was your case 1. Okay. Now, second case is what, that saddle point if lambda 1 and lambda 2 are real, unequal and are opposite sign, and that correspond to your case 2, which we have already discussed. Now, stable node if lambda 1 and lambda 2 are real, equal and negative, and unstable node if lambda 1 and lambda 2 are real, equal and positive. This was our case 3. Now, and then stable center if lambda 1 and lambda 2 are purely imaginary, that is what we have discussed as case 5 here. And stable focus if lambda 1 and lambda 2 are complex conjugate with negative real part, and unstable focus if lambda 1 and lambda 2 are complex conjugate with positive real part, that was our case 4 here. Please, if you look at these result, then stable and unstable depend on the real part. Whether real part is negative, then it is stable, if real part is positive, then it is unstable, and then we can simply say that it is node if it is real, unequal, and so if we look at 1, 2 and this thing, then node means if lambda 1 lambda 2 are real, okay, and of either equal with equal or having the same sign here, and it is saddle point if they are real, unequal and of opposite sign, and in center and focus depending on whether they are complex. So, if they are complex, then it will form a center if it is purely imaginary, otherwise it is focus here. Okay. So, that is what we have summarized, which we have given discussed as case 1, case 2, case 3, case 4 and case 5. So, with this we say conclude that for the linear system your phase portrait and the critical point and behavior of the critical point is done with this. Now, let us go to stability of nonlinear system here. So, consider nonlinear system dx by dt equal to ax plus by plus p1 x comma y and dy by dt equal to cx plus dy plus q1 x comma y here, where a, b, c, d, p1 and q1 satisfy the following condition. First thing is that a, b, c, d are real constant and a, b determinant of a, b, c, d is non-zero. And second condition is that p1 and q1 are having continuous first partial derivative of all x y and are such that limit x comma y tending to 0 comma 0 p1 x comma y divided by under root x square plus y square equal to 0, and similarly limit x y tending to 0 0 q1 x y divided by under root x square plus y square is equal to 0. And if you recall, this kind of a linear system is known as weakly nonlinear system here, and here we are assuming that these p1 and q1 are such that it will vanish at origin here. So, also consider the corresponding linear system. So, corresponding linear system is dx by dt equal to ax plus by and dy by dt equal to cx plus dy. What we want to conclude from this, that though it is a nonlinear system, but still the behavior of the critical point 0 comma 0 is very much similar to the behavior of the critical point of the corresponding linear system, as we have already pointed out. So, here we simply say that consider the corresponding linear system by neglecting the term p1 and q1 here, and let both the system have an isolated critical point 0 comma 0, that we as we are assuming that p1 of 0 comma 0 is 0, similarly q1 of 0 comma 0 equal to 0 here, and let lambda 1 and lambda 2 be the roots of the characteristic equation which is corresponding to the linear system, that is lambda square minus a plus d lambda plus ad minus bc equal to 0. Then we have already discussed the behavior of the critical point 0 0 0 completely for the linear system. Now, we want to conclude from the behavior of the linear system the behavior of the 0 comma 0 for the nonlinear system. So, the say results are given as follows: the nature of the fixed point 0 comma 0 of both the system is same in the following cases. First, that 0 comma 0 is node for both the system. It means that lambda 1 and lambda 2 are real, unequal and of the same sign. So, if lambda 1 and lambda 2 are real, unequal and of the same sign, then 0 comma 0 is node for both the systems, and if lambda 1 and lambda 2 are real, unequal and of the opposite sign, then 0 comma 0 is saddle point for both the systems. So, it means that if it is a real, unequal, whether it is of same sign or opposite sign, behavior of 0 comma 0 is same. It means that if it is node for one system, then it will be node for the other system as well, and if it is a saddle point for one system, then it is saddle point of the other system. So, for real, unequal, behavior is same. Now, 0 comma 0 is node for both the system if lambda 1 and lambda 2 are real and equal, and the linear system is not such that a equal to d is not equal to 0 and b equal to c equal to 0. And if you look at, this is the case corresponding to star shaped node. So, it means that if 0 comma 0 is node, but not corresponding to star shaped shape, then also the behavior of linear and nonlinear system is same. So, it means that in the case when it is a node, but not a star shaped node for the linear system, then also the behavior of linear and nonlinear system is same. And last case is that if lambda 1 lambda 2 are conjugate complex with a real part not 0, that is case 4, then not only 0 0 is a spiral point for both the system. So, then if lambda 1 and lambda 2 are complex conjugate with real part not equal to 0, then also 0 comma 0 is a spiral point for both the systems. And if you look at these things we have already proved as a part of theorem. Here we are just visualizing it. Okay. So, let me recall this. So, if node not corresponding to star shaped, then it is both for linear and non-linear system, and corresponding to say focus spiral point, we simply say that if lambda and lambda 2 are complex with the non-zero real part, then also the behavior of the critical point will correspond to in both the cases. Like if it is say spiral point for linear system, then it will be spiral point for the non-linear system. Now, the critical point 0 comma 0 of the non-linear system is not necessarily of the same type as that of the linear system in the following cases. So, here in these 4 cases they are exactly similar, not exactly, it is similar to each other, but in the given 2 cases it may not be same. So, if lambda 1 and lambda 2 are real and equal, and of the linear system is such that A equal to D not equal to 0 and B comma C equal to 0. So, then 0 comma 0 is node of 18, the point 0 0 may be either a node or a spiral point for 70. So, it means that in this case when lambda 1 and lambda 2 are real, equal, and it is corresponding to the case of diagonalizable matrix, then for linear system it is a star shaped node, but for non-linear system it may be node or maybe spiral point. So, this case we are not here in this case when lambda 1 and lambda 2 are equal and corresponding to diagonalizable matrix, then behavior may not be same. And second point, if lambda 1 and lambda 2 are purely imaginary, then 0 comma 0 is a center of linear system, as we have already discussed as in case 5. The point 0 comma 0 may be either a center or a spiral point of non-linear system. So, in these 2 cases your behavior of critical point may not correspond, right. Now, let us take one simple example based on this. So, determine the type and stability of the critical point 0 comma 0 of the nonlinear system here. So, dx by dt equal to 8x minus y square and dy by dt equal to minus 6y plus 6x square. So, here it is, if you look at here 0 0 is the critical point for both the linear as well as the corresponding linear part, that is dx by dt equal to 8x and dy by dt equal to minus 6y. So, this is a nonlinear part and this is the associated linear part. So, determine the type of the critical point 0 comma 0, we consider the linear system, this is 8x and minus 6y, and the characteristic equation of the linear system we can find out like this: lambda square minus 2 lambda minus 48 equal to 0, and it is coming out to be 8 and minus 6. So, it is real, unequal and of opposite sign. So, we simply say that for the linear system your critical point is simply 0, critical point is a saddle point. Now, to conclude about the nonlinear system, we observe that the determinant is non-zero and P1 equal to minus y square and Q1 equal to 6 square have continuous first order partial derivatives for all x comma y, and such that limit x y tending to 0 0 minus y square upon x square plus y square equal to 0, and limit x y tending to 0 comma 0 6 x square upon x square plus y square is equal to 0. So, it satisfy all the condition of the previous result. So, it means that here we have assumed that your weakly nonlinear system satisfy these equation these condition, that A, B, C, D are real constants as the determinant is non-zero. Second, P1 and Q1 have continuous first order partial derivative with the condition. So, here we have seen that in example it satisfies all the condition listed here. So, it means that that in this case the behavior of the critical point 0 comma 0 will correspond. It means that we have already seen that 0 comma 0 for the linear system is saddle point. So, for the nonlinear system also your 0 comma 0 is a saddle point. So, to show that limit x y tending to 0 comma 0 6 x square upon under root x square plus y square equal to 0, you may use the epsilon delta condition here. So, this I am not putting here, but you can simply say that to show that limit is equal to 0, you can say that given any epsilon greater than 0, there exists a delta such that mod of 6 x square upon under root x square plus y square minus 0. This we want to show that it is less than epsilon, provided that the distance means x square plus y square is near to 0 comma 0. Okay. So, for that you simply write x equal to r cos theta, y equal to r sin theta. Whenever you have this term x square plus y square, you can simply use x equal to r cos theta, y equal to r sin theta, that is polar coordinate system. So, we can simply say that this is nothing but 6 r cos square theta. Now, cos square theta is something which is less than or equal to 1. So, we can say that it is less than 6 r, which is nothing but 6 under root x square plus y square. Now, if this quantity is less than epsilon less than delta, then I can say that this is what 6 under root x square plus y square is this, we want that it should be less than epsilon. And so, it means that if we simply say that whenever mod of x is less than delta, mod of y less than delta, where delta you can assume epsilon by 6 root 2, then this quantity can be made less than epsilon, and hence we can say that limit x y tending to 0 comma 0 6 x square upon under root x square plus y square equal to 0 here. So, in a similar way you can prove the other way other also, that limit of x y tending to 0 comma 0 minus y square upon under root x square plus y square is equal to 0. So, therefore, we conclude that the critical point 0 comma 0 of the nonlinear system is also a saddle point and it is unstable, right. So, with this we conclude our lecture here, and in next lecture we will discuss something more about nonlinear system, which is not weakly nonlinear system. Here we have seen that the behavior of critical point in the linear system, and in a similar way we can say we can conclude something about weakly nonlinear system, and what happen if we have a general nonlinear system, what we can say about the critical point, or can we say something or not. So, that we will try to discuss in next lecture. Thank you very much for listening. Thank you.